The second component of an SMS is safety risk management. We've already seen the 5 major elements of SRM, so now let's see how they work in detail. The objective of an SMS is to provide a structured management system to enable us to make decisions on controlling risk in our operations. Once hazards are identified and their related risks analyzed, an organization can focus its resources on eliminating or mitigating those hazards that pose the greatest risk. This is what SRM helps us to do. As previously mentioned, a safety management system controls risk and assures that the controls are working. Safety risk management is how we do that first part, controlling the risk. Safety risk management starts with the identification of hazards, which are then analyzed to determine the risk to the company. The information is assessed to determine if the risk is acceptable or not. And finally, unacceptable risks are mitigated through the implementation of risk controls. Each organization must define its own acceptable levels of risk and what levels of management are authorized to accept various degrees of risk. Safety assurance, that's where the whole operation is then monitored for the effectiveness of the controls and for the appearance of new hazards. Risk management is applied at 2 primary levels. The first is the process level, and the second is at the operational level. Process risk management has 3 main areas to consider. Policy, what needs to be done. Many risk decisions should be part of company policy, the result of careful deliberation about a broad range of situations. Policies convey to employees what they should do in various situations. For example, many operators prohibit circling approaches in instrument weather conditions. The second area is procedures, how to do it. Employees should be given procedures that have been developed in ways that take risk into account. For example, the selection and sequence of items on a checklist for operation, maintenance, and cabin safety help control human error. And third, controls, such as required inspection items, which defend against possible errors that could occur in the operation. Operational risk management is comprised of operational control and crew or team decision-making. The operational control aspects involve how risk management is employed on a mission-by-mission basis. Oversight by dispatchers, supervisors, flight followers helps to ensure that potentially hazardous conditions are identified and controlled during specific operations. Crew or team decision-making starts with frontline personnel, such as pilots, mechanics, cabin crews, and controllers. They must have tools and procedures that help them make decisions. We know the pilot in command is the final authority, but several levels of risk control should be employed. Organizations need to pay attention to all levels of risk management. System description, also called system description and task analysis, is the first step in the SRM process. This step is often skipped or done hastily, yet it's one of the most valuable activities an organization can do. It allows the company to understand what they do, who does it, and in which environment they achieve company goals. Pilot project participants have shared that they have found enormous value, financially and of efficiency, from taking the necessary time to complete this step. What is system description and task analysis? It is a design function involving the whole organization. It is a predictive method of hazard identification. When the dots do not connect, there is probably a hazard lurking there. Design it out. It is the foundation for a sound safety analysis. If you don't know who's on the team and what position they play, how can you expect to accomplish the goal? When is it used? It is used during the implementation phases of SMS, as you design your SMS. It is used to develop operational processes. It is used when a new hazard is identified. And it is used in conjunction with all operational changes, again, as you design your new system, process, or procedure. Who uses system and task analysis? You need an appropriately diverse team, stakeholders, and subject matter experts. Remember, the system description and task analysis need only be as complex as needed to design procedures, develop training, identify hazards, and to prepare documentation for employees and other users. The level of detail required will vary depending on the complexity and safety criticality of the processes involved. Detail beyond this point is not necessary. In past trainings or discussions, you've probably learned the importance of identifying facts versus inferences versus judgment. System and task analysis must concentrate on being factual so you can accurately consider any process's potential for causing a problem. Here we break those processes down into activities, the things people do, and workplace conditions. Now, why are these processes, activities, and workplace conditions important? Well, first let's take a look at workplace conditions, and then at the human activities. Here are several typical workplace conditions. These conditions exist for all processes. Unsatisfactory conditions can become hazards that exist before an accident. Understanding these factors and their effects on safety performance will help us to control them, which is the ultimate goal in managing risk. A poorly written or incomplete procedure can be rewritten. The marginal training class can be improved. The broken, missing, or worn-out tools or equipment can be replaced or serviced. The hangar that is poorly lighted can be upgraded. These factors and many more workplace conditions have been contributing or causal factors to many accidents. If an organization can manage these, they will likely be managing their risk. And this leads us to the system safety attributes. In the earlier safety policy portion of the presentation, we said one of the keys to a system safety approach is to make sure safety is built into our systems. So what do we look for in the design of a system? A primary component of any well-designed functional system is the adequacy of certain attributes. These attributes affect both safety and quality management systems and have been documented in both the national and international publications. So what are these attributes? Responsibility. Who is accountable for the safety and quality of the process activities? Authority. Who has the power to establish and modify process procedures? Procedures. Are there clear instructions for members of the organization? Controls. Are the administrative processes or supervisory controls adequate to ensure the activities produce the correct results? Process measures. Is there a way to determine whether a process is being performed according to the established procedures and achieving the desired results? Safety ownership. Do employees try to work together to identify and correct safety concerns? Interfaces. Are there strong interrelationships between the processes? Does the left hand know what the right hand is doing? Now for a process flow that can be applied to any process in an organization. We'll illustrate two things. First, how the process attributes fit into a process flow, and then we'll show how the flow applies to a real-world workplace. First, the process itself is a set of interrelated or interacting activities, things that people do that transform inputs into outputs. We add inputs, which can be external, a decision by the company to open a new station, or internal, the output from a previous process. For example, the flight crew calling for de-icing triggers the station de-icing crew to start their process to de-ice the aircraft. Notice that inputs are an interface process attribute. Next we ask, who's in charge? And who can make changes to the process, and who can accept risk on behalf of the company? Then we need procedures to direct or guide the things that people do. A procedure is a specific way to carry out an activity or a process, another process attribute. Controls. procedures, steps, or practices that are designed in to keep processes on track so they'll achieve their intended results. And now we get to outputs, the product or end result of a process, which can be recorded, monitored, measured, and analyzed. Outputs may be the input for the next process area in succession, so it's important to get it right. Outputs contain the input interface attribute, the safety ownership attribute, and the performance measures. This model is a simple input, activity, output flow, showing where the process attributes affect a process. Now we'll demonstrate how the process flow might look in the real world. In addition to the internal and external inputs, we see customer requirements and materials, especially if your output is a product. On the control side, we see the obvious controls of laws, regulations, and standards. Training is also a control, as are the books, aids, and software we use. How about the people, the folks doing the job and those in charge, plus their facilities, equipment, and tools? And finally, the environment in which everything has to work. Combine all of these and you generate the output of a product or service. We've described system analysis, workplace conditions, and attributes that should be considered. So now let's look at the human side of the equation and some conditions that have potential to cause harm. Because humans operating in the system account for the majority of active failures, either contributing to or being blamed for most accidents, we'll examine conditions relating to human error as we continue with SRM and attempt to manage the things we can manage. Here are some examples of conditions that contribute to errors, which can result in active failures. These conditions are typical findings when reviewing incidents or accidents. They also exist in a predominant number of daily errors that haven't yet resulted in an undesired event. You can no doubt think of examples of each of these that you've experienced or seen. These are a few more examples of conditions that lead to errors. Many of these conditions are subjective and not factual, therefore making them difficult to address directly. Adjectives such as poor, inadequate, and lack of, at best, may indicate a trend. However, service providers must learn to manage the risk associated with these conditions. This example shows how activities and workplace conditions can be depicted for de-icing an aircraft. Human activities are on the left and workplace conditions on the right. Human activities and workplace conditions are independent lists. While not an extensive, exhaustive list, this type of thought process and progression is helpful in an organization's development of an SMS. Breaking down the process steps into manageable pieces is an effective way to capture and track the information. The next element of SRM, called hazard identification, is used to determine the aspects of the system and environments that present hazardous conditions. Consider these points. Hazards are often erroneously identified as consequences. Hazards are not events. As such, hazards do not occur, but they exist in the environment. Any workplace condition or set of conditions may or may not be a hazard. Workplace conditions become hazardous conditions when they singly or in combination present the potential for harm. For conditions to be hazards, there must be some type of exposure to aviation operations. As an example, not all power lines or telephone wires are hazards. However, the wires in this photo are a hazard because they are in a place where aviation operations come close enough for airplanes to be tangled up in them. We just said workplace conditions become hazards when they singly or in combination present the potential for harm. This diagram shows how our knowledge of workplace conditions flows into the hazard identification process. Deficient conditions impacting activities. We interpret the knowledge we've gained about the workplace conditions and apply them to identify hazards that could cause harm. Then we add our knowledge of the human activities to our knowledge of the hazards to infer what could cause active failures. System and task analysis must concentrate on being factual, so that accurate inferences about their potential for causing system failure can be accomplished. Now we progress from hazard to risk analysis. A hazard is a condition that may have an adverse consequence. Risk is a hazard that's been analyzed for the severity and likelihood of the consequence. That is, workplace conditions and active human failures, along with the potential consequences, must be analyzed to determine how likely they are to happen and how bad they would be if they did. The more adverse the workplace conditions, the more likelihood of active failures and a resulting accident. This graphic demonstrates the progression from hazard to risk. After identifying the presence of a safety hazard, analysis is required to identify active failures that have the potential for an adverse consequence. The likelihood that an adverse consequence will occur is directly proportional with increased exposure to the hazard. Likelihood is typically linked to an active failure and further a set of underlying adverse workplace conditions. Now, while we may have data to establish the likelihood of failures, based on past experience, usually this will be based on the judgment/decision of those involved, another reason for the need for operational experience in the process. Active failures are often cited in probable cause statements or audit reports. The probable cause of this accident was the pilots, crews, mechanics, controllers, etc. failure to. Be sure to consider all possible adverse consequences that could result from the active failure. One hazard can have multiple consequences, each with different likelihood or severity values. Also, that severity is driven by the consequence. For instance, if the possible outcome of errors during an instrument approach is controlled flight into terrain, the consequences will almost certainly be catastrophic. On the left are listed some possible active failures that can be the direct result of human activity. These failures should be related to the process and/or one of its underlying activities. We've also postulated potential consequences that could result, as an example that can be helpful for an organization going through this process. Risk assessment is a decision or judgment process based on human knowledge and past experience, but guided by a structured process. It determines the level of risk to assist in bottom-line decision-making. A risk matrix is a tool for looking at combined effects of likelihood and severity in order to prioritize resources and aid in decision-making. It's important to remember that a risk matrix is not risk assessment. It is only a tool to help determine which risks to address in what sequence. The risk assessment is a human activity of applying knowledge and experience in making judgments on likelihood and severity values. Color codes can help determine the acceptability or tolerability of risk. Is the risk acceptable? If so, the system can be put into operation. If not, there's more work to be done. Typically, tolerability and intolerability are indicated by using the color codes of green for acceptable risk, yellow for acceptable with mitigation, and red for unacceptable risk. The FAA does not require that there be a certain number of severity or likelihood levels and leaves the construction of the matrix up to the organization. At this point, risk assessment has two options possible. The risk is either acceptable or not acceptable. If judged acceptable, the SRM process is complete and the risk moves on to the safety assurance process for monitoring. If the risk is not acceptable, then risk controls are required to mitigate or reduce the risk. Risk controls are sometimes called defenses or barriers. While we may be able to reduce the severity, say by using protective equipment, in most risk situations, we'll only be able to reduce the likelihood or probability that something bad will happen. We'll do this by reducing the likelihood of an active failure, mostly human errors or equipment malfunctions. As an example, the use of anti-skid tape on a maintenance stand reduces the likelihood that someone will slip on the platform. Installing railings reduces the severity. If someone does slip and fall while working on the stand, they may not be hurt as badly. If the environment includes working in the rain, wind, and at night, what will the conditions do to our likelihood and severity? Likelihood will increase, but severity may not. Risk controls are usually applied to working conditions, things that can be managed. The purpose of risk controls is to develop barriers or defenses to mitigate safety risk down to an acceptable level. Once a risk control is developed, it should be run back through the SRM process to ensure it will function in the system, doesn't introduce other hazards, and accomplishes what it was designed to do. When risk has been found to be undesirable or unacceptable, control measures must be introduced. The higher the level of risk, the greater the urgency. The level of risk can be lowered by reducing the severity or likelihood of each possible consequence. There is no such thing as absolute safety, so risks have to be managed to a level that is low as reasonably practicable, which means that the risk must be balanced against the time, cost, and difficulty of taking measures to reduce or eliminate it.